Okay, welcome. Good morning, everyone. I'm Eric Mas from IRIDeS. I will be your moderator for today. So this is a webinar. It's being streamed via Zoom. And the video of this seminar will be shared in our Facebook page and other homepages of IRIDeS at a later date. So our topic for today is findings from the 2024 Noto Peninsula earthquake and tsunami. And first, I would like to invite Professor Yuichi Ono, Deputy Director of IRIDeS, to open this seminar.
Good morning, everybody. Welcome to IRIDeS again. I already greeted many of you, but I think there are some newcomers today. So let me state again for the what IRIDeS is and so on. My name is Yuichi Ono, as Eric introduced. I'm Deputy Director. There's two Deputy Directors and another Deputy Director is sitting, the Professor Koshimura. So we have two Deputy Directors in here. Our director is absent today, but we have about 60 professors, researchers, and the total in this building, 200 people are working. And everybody is doing some kind of disaster reduction study. We are multidisciplinary institute, and as I said the first day, we have developed in 1 year after the 2011 tsunami here. So after tsunami happened, quickly we developed this institute. I came to this institute 1 year later, but there was an effort to develop this institute. In Japan, historically speaking, after large, huge disaster, there was a government effort to develop the scientific research center. Oldest one is in Tokyo University's Earthquake Research Institute, developed in right after the 1923 Kanto earthquake, Tokyo earthquake. So they developed the Earthquake Research Institute. Then the next big one was the Kyoto University, established a disaster institute and after the typhoon in, I think, 50s or 60s. So they have 70th year anniversary recently. Then IRIDeS is a baby in comparison with other institutes like that. But we quickly developed this institute. Our mission is to do the disaster science, but for the huge disaster event, which could happen very rarely, how do we deal with that? And in 2011, there are a few things happens that citizens, normal citizens, are not so much trust in the scientific world at the time. Then we had a big challenge to tackle. The one was even the seismologist could predict the earthquake of 9.0, huge earthquake. Not even seismologists could predict that. Then another one was in the scientific community, we knew historically the tsunami reached 2 to 3 kilometers, even 3 kilometers inland towards the land. So that was some scientists knew, but in public, many people are not understanding that very well. So that was another thing. Then nuclear power plants accident in Fukushima. So we have a difficult time in 2011, just after the tsunami happened. So we gathered the efforts, the knowledge and wisdom together in Tohoku University. That's a starting point. Then another epoch-making thing was in 2015, there was a big UN meeting to talk about disaster risk reduction. Then I think 6,000 officials gathered in this, not in this campus, but the 2 subway stations down, you see the International Conference Center. That's where the negotiation took place. I think some of you were there for negotiation and for symposiums and so on. So that was a Sendai framework for disaster risk reduction. This Sendai framework for disaster risk reduction is a real overall sort of a scheme, a framework for disaster risk reduction. So our institute is also trying to implement the Sendai framework. Then, as you know, the Sendai framework is including the many issues, but one word in Sendai framework, one word is investment in disaster restoration. We are in the increasing risk world with climate change and others, but the investment level is not catching up with the increasing risk. So Sendai framework is calling for the importance of that. Then for IRIDeS, we are trying from the scientific way to implement the Sendai framework and so on. So that's a little bit of a history of IRIDeS contributing to the Sendai framework. Then Sendai framework will continue until 2030, the same as SDGs. So we want to make an international contribution. That's how we hosting your event in the UNESCO IOC event here today and this week. So very happy to have you and I'd like to welcome you. And I'm sorry for this snowy weather today, which is not expected, but you may have a 6 centimeter of snowfall until tomorrow morning, according to the JMS forecast, recent forecast. So when you wake up tomorrow morning, you may have to walk a little bit of snow, accumulated snow. Be careful not to be, having an accident. And after this seminar today, this seminar today is about the Noto Peninsula earthquake and tsunami. And we have renowned researchers who are into this subject, Professor Koshimura and Eric and Adriano-san and so on, and Anamata Sensei here. And after that, as you know, we are going to the little bit of experience in the tsunami-affected area. We are, I think, having a lunch in the Natori area. That's where the recovery of the small business and restaurants. So that's where you experience to eat some food there and some, I think, seafood and so on. Then we moved to the Arahama area in the Sendai city. The Arahama community was totally washed away by tsunami, inundated. So nobody lived there anymore. They relocated towards inland. But there's a school building, Arahama Elementary School. That's where I think 500 people evacuated, more than 500 people evacuated, and all the neighbors are trying to be away from a tsunami and under the tsunami warning in 2011, March 11th. Then that school building was converted to a museum now. So you can see what happened and you experience that elementary school. So that's, and then you come back to the Sendai station instead of here. So it's Sendai station around before 6 o'clock, right? 5:40. So before 6 o'clock, you should be at the Sendai station. Then you go to the hotel for the tomorrow morning. So that's for information package for today. And one caution: this Friday is a national holiday in Japan, so the restaurants are closed for the lunch, and we are checking, but the one convenience store just near the train station, subway station is open. So you may be able to buy bento, lunchbox, or the onigiri, the rice balls, and bread, and some sandwiches. So please be careful that on the Friday. We didn't expect that, but it is. So having said this, let us enjoy our special session on the tsunami warning system and Noto earthquake case. Eric, please.
Thank you. Thank you very much for your words. Before we move to the first presentation, I would like to let you know that there are 2 microphones. After the presentation, we have a small time for questions. So if you feel to have a question, you can turn on the mic and make your question. This is a webinar, so we only receive questions from the floor. So all the pressure is in you guys. There is no question from online, okay? So if that's okay, our first presentation comes from the Associate Professor Yusaku Ota. He's from the Graduate School of Science. He's actually on a business trip, but he kindly agreed to join us online. He's from the Research Center for Prediction of Earthquakes and Volcanic Eruptions, specifically the Crustal Physics Laboratory in Tohoku University. So he will share with us the 2024 Noto Peninsula earthquake and its fault model from GNSS observation.
Okay, thank you, Eric Sensei. Thank you very much for your introduction. I'm currently attending another conference in New Orleans, Ocean Science meeting, and so I will not be able to participate this great seminar. Anyway, so today I'd like to introduce the co-seismic fault model of the 2024 Noto Peninsula earthquake using the very dense GNSS network. And also, I introduced the transient cluster deformation that preceded it. As you know well, a massive magnitude 7.6 earthquake struck the Noto Peninsula on just New Year's Day this year. This is a mechanism solution for major earthquake around the Noto Peninsula with aftershock distribution of the magnitude 7.6 earthquake. From this figure, you can see that the magnitude 5.4 and magnitude 6.5 earthquake occurred in 2022 and 2023, respectively. In this region, there was a very distinct cluster of the earthquakes and associated transient cluster deformation that has continued since the end of 2020. So we will explain this preceding event before modeling the current earthquake. In Japan, GeoNet, operated by Geospatial Information Authority of Japan, GSI, is used for cluster deformation monitoring. This black rectangular denoted the GeoNet site distribution around the northern part of the Noto Peninsula. And this red circle denoted the very high activity of the earthquake. So its spatial resolution, this GeoNet spatial resolution is clearly insufficient for events such very localized events. But in Japan, private mobile carrier SoftBank is operating its own GNSS observation network starting at the end of 2019. This green rectangular denotes the site distribution of the SoftBank original GNSS network. In addition to this data, we also use the campaign GNSS site established by the Kyoto and Kanazawa University. Blue and pink color indicated the site location of the GNSS site operated by Kyoto and Kanazawa University. This allows us to discuss this transient cluster deformation with an exceptionally dense GNSS observation network, which has never been done before. This is a snapshot of the cluster deformation of each time period. The first time period is the end of 2020 to March 2021. So you can, this vectors denotes the horizontal displacement, and red and blue rectangular denotes the vertical displacement. So you can confirm the wide area of the horizontal deformation in the northern part of the Noto Peninsula. The horizontal cluster deformation is confirmed an expansion. And the vertical cluster deformation is also confirmed as the uplift center of the epicenter. In the second time period, the cluster deformation is slightly smaller than the previous time period. Time period is March 2021 to June. The third time period, June 2021 to June 2022, the horizontal deformation is larger than the previous one, and the vertical deformation denoted by this red rectangular shows the largest. The fourth time period is 2022 June to March 2023, show that the vertical deformation remains relatively large, but the horizontal one is decreasing. We modeled and interpreted this cluster deformation in each time period. Left-hand figure shows the schematic in the underground. This part is the northwest and the southeast. In the first time period, we estimated that there were near horizontal faults of opening motion to explain the direction of expansion in both of the horizontal and the vertical deformation. This port corresponds to here. It's this port opening. In the next time period, the port position is considered to have moved slightly upward. Although the amount of the deformation is relatively small. In the certain period, the port is supposed to have expanded more shallower portion. And this was inferred from the ratio of the amount of the vertical to horizontal deformation. And finally, it is estimated that the shallower port opening and slip remained and were active. So this result is very strange. That is that in this area, which is not because here is not volcanic area. But the source of the deformation are considered to be these open ports. As a possible cause of this, we considered fluid from the depths, specifically were water intrusion. Anyway, so it is important to note that the region was experiencing these preceding events, which were captured by very dense GNSS observations. So it is slightly difficult to discuss the relationship between this preceding event and the magnitude 7.6 event. So many researchers still discuss the relation between these two events. Okay, let's move on to the estimation of the co-seismic fault model. This earthquake was an inland earthquake that occurred in the crust. Therefore, fault plane must be assumed in advance. In this case, we assume the fault plane with final fault patches at a station with many observation sites and less sensitive area with coarser fault patches, as shown in this left-hand figure. And the green one is GeoNet, and the blue one is the SoftBank, and the red one is the campaign GNSS site operated by universities. And the right-hand figure shows the co-seismic displacement field of the horizontal and the vertical. So you can confirm this unit is 1 meter, so maximum displacement more than 2 meters in the horizontal, and in the vertical component, you can confirm the very clear uplift along the northern part, northern coastline of the Noto Peninsula. But this large co-seismic uplift rapidly decrease to the middle of the Noto Peninsula. We do not have time to discuss the estimation methodology in detail, but we will utilize the data-driven estimation method based on the Bayesian statistics to estimate the co-seismic slip distribution as a fault plane. I mentioned earlier that in cases such as this inland earthquake, the assumption of the fault plane is essential. The left and right figure show the co-seismic slip distribution estimated assuming the southwestern fault plane dip of 25 degrees and 55 degrees, respectively, and a comparison between the observed and calculated displacement in each side. And the black and white vectors represent the observed and calculated horizontal displacement. Several points are notable. For example, the station SZOT here, with a small dip angle of the port, can explain the horizontal displacement, basically, but significantly underestimate the vertical deformation, half of the observed one. Conversely, if the dip angle of the port is large, the vertical deformation can be explained, but the horizontal this seismic deformation cannot explain. To resolve these conflicting conditions, the fault plane assumption is reconsidered. So in this region, a database of faults in the sea area has been constructed by Jamstack. In this database, the fault model in this region restricts with a high dip angle at shallower depths and a low dip angle at a deeper depths. Based on this information, the figure on the right reflects these factors for the fault plane on the southwest side. In the shallower portion, have a very steep dip angle, but more deeper part portion, we assume that 25-degree dip angle. This is the fault slip, the coseismic fault slip distribution model estimated assuming the district fault plane. The assumption of high dip angle fault plane has improved the agreement of the vertical displacement along the northern part of the Noto Peninsula, and horizontal deformation. It actually does not fully explain the observation data, especially this northward displacement in the two sides. But anyway, so based on this obtained result, we can confirm that mainly two coseismic slip patches. And this eastern part of the coseismic patch is basically purely dip slip. But this western side of the coseismic slip shows contains strike slip components. The vertical deformation field expected from the estimated coseismic fault model is shown. The right figure shows the vertical deformation field estimated from the synthetic aperture radar data for comparison. It's calculated by GSI. Our model can explain the two large uplift area basically. However, it does not fully explain the uplift area extending southward on the southwest side, this area. Finally, a comparison of the assumed fault plane with the determined hypocenter estimated by the double difference approach is shown. And this one is the southwest segment, and this one is the northeastern segment. The direction is the southwest to northeast. On the southwestern side of the fault, and the aftershock distribution and the fault plane denoted by this solid line, coincide well, except in the most southwesterly region around here. For the northeastern part of the fault, it is very difficult to discuss the detailed comparison due to the low accuracy of the hypocenter determination and coseismic fault distribution because there is no GNSS site around here. At present, aftershocks are being observed using ocean bottom seismometer around here. Integrated analysis of this data will enable more detailed comparison in the future. Okay, let me summarize my talk. We reviewed unsteady cluster deformation and its modeling in the Noto Peninsula. A coseismic slip distribution model was estimated using a very dense GNSS observation network. The model assumed to be historic fault geometry basically explain the observed data. But please note that this coseismic fault model is still preliminary. In future work, we will compare the data with synthetic aperture radar data and the other geophysical surveys to develop the more precise model. That's all. Thank you very much.
Thank you very much, Ota-sensei. Okay, so we have time for some questions. If you guys would like to ask something, you can just go to the mic or raise your hand and take one of. There's two mics here in the middle of the aisle. Oh, yeah, thank you, Don. She's gonna give it to you. Or he. Turn on the mic, please. Thank you.
Okay, thanks for the presentation. It's very interesting. I was wondering if I've seen the model with the enriched fluid enriched lower crust and so on. If there is some been some attempts of modeling with the velocity or attenuation tomography to understand the crustal structure and the faulting mechanisms. Thank you.
Yes, very good question. Thank you very much. Very good question. So I cannot explain the detail in the presentation, but we already confirmed that, for example, this area shows a very low resistivity, and also we confirmed the very low S-wave velocity. So based on these structural characteristics, we conclude this area contains a very rich fluid. So we conclude this activity related to the fluid intrusion.
Thank you. Any other question? We still have some time. Okay. There's one more question. Oja.
Thank you very much, Professor. Forgive my daring question, and thank you very much for the presentation. Are we perhaps witnessing the very early stages of a birth of a volcano in geologic timescale, and that activity triggering the fault mechanism? Would you comment on that?
Okay, thank you very much. I also skipped this point. So some of the geologists already pointed out that here is we can confirm the buried caldera. So it is difficult, but maybe this this activity may be related to the historical, no, not historical, very geological volcanic activity.
Okay. Anyone else? We have more time. No? May I ask something, maybe? You were talking about listric faults. How common are these listric faults? Are they identified in Japan? Are these more dangerous than normal faults? Or how can you let us know a little bit more about listric faults?
Yeah, so actually, I'm not so professional of the geological aspect, but some of the area have such kind of the historic fault, especially along the eastern edge of the Sea of Japan. So. So we need to pay attention to this historic fault plane in the future.
Okay, thank you. Okay, no more questions. Shall we move to our next presentation then? Okay, Professor Ota, thank you very much for joining us.
Very much. Thank you.
Have a good sleep. So we move to our next presentation. It's coming from Mr. Shingo Shida. He's from the Japan Meteorological Agency, Senior Coordinator for International Earthquake and Tsunami Information. He's going to talk us about on the tsunami warning system and the 2024 Noto Peninsula earthquake case. Please.
Thank you, Eric Sensei. Hello, my name is Ushida. I work for Japan Meteorological Agency, JMA. Thank you for coming today in the snow, as predicted by JMA, as Dr. Ono introduced at the opening session. Anyway, with the experience of the Tsunami National Contact of Japan, I am very honored to have the opportunity to share the insight with you today. Okay, today's I will talk about three topics. Firstly, I would share with you Japanese tsunami standard operation procedure. Next, I will explain the tsunami warning issued for the Noto earthquake. The earthquake was occurred January 1st this year. JMA issued tsunami warnings. Finally, I would like to review the tsunami height following the Noto earthquake. Okay, let's start with the Tsunami Standard Operation Procedure of JMA. This figure shows the Japanese earthquake monitoring networks. JMA utilizes the data from the JMA on seismic station, not only JMA seismic station, but also the equipment installed by university and research institute, such as IRIDE. These data are transmitted in real time, so JMA can determine the hypocenter and the magnitude using these data. As in the case of the earthquake monitoring, JMA and Research Institute cooperate in tsunami networks. Sea levels are measured not only by tidal gauge at coast, but also GPS, but also by GPSV offshore and sea pressure sensor on the sea floor. These data JMA collect these data in real time. Japan has experience of the devastating damage of the local tsunami that comes immediately after the earthquake. So we think it is very important to issue the tsunami warning immediately. So Japan conduct tsunami warning operation using tsunami database. This slide shows the procedure of tsunami warning of Japan. JMA has simulated the tsunami in advance and stored the result of 100,000 scenarios in advance. The tsunami database has contains the tsunami amplitude and arrival time calculated by numerical simulation. Once earthquake occurred, JMA determines the magnitude and hypocenter immediately. Then JMA searches the tsunami database and pick up the most appropriate scenario from the database. Using the result, JMA issues the tsunami warning. This is the sequence of tsunami warning. After occurrence of the earthquake, JMA determines the hypocenter and magnitude immediately. As mentioned previously, JMA issued tsunami warning using tsunami database. The warnings issued by JMA communicate to the disaster prevention agency and media immediately. So the goal to issue the tsunami warning is within 3 minutes after detection of the earthquake. And if reevaluated magnitude exceed the initial value, GMA update the tsunami warnings according to the magnitude. GMA takes in account the sea level observation to cancel the tsunami warnings. This is the sequence of the tsunami warning in GMA. Okay, let's move on to the Noto earthquake case. Before showing the case for the Noto earthquake, I would share with you the outline of the tsunami warning of Japan. In Japan, there are 66 regional blocks for tsunami warning and advisory. And we set 3 categories of warnings and advisory. According to the estimated tsunami height with its color. Violet means major tsunami warning. Red means tsunami warning. Yellow means tsunami advisory. Please keep in mind the meaning of the color as they are used following the explanation. And red X in the map is indicates that epicenter of Noto earthquake it occurred January 1st this year. Remember the location as well. This slide illustrated the actual tsunami warning issued by GMA for the Noto earthquake. At first, upper right, upper left, I mentioned as upper left. At 16:10 Japan Standard Time, January 1st this year, the earthquake occurred. Then, GMA determined the magnitude to be 7.4. Using tsunami database, GMA issued the tsunami warning at 16:12. We could issue the tsunami warning within 3 minutes. This picture is actual tsunami warning published on the GMA website. And this warning was reported by media immediately. At that time, I was in the home. I was at the home in Tokyo. Tokyo is apart from the Noto Peninsula, about 300 kilometers. I felt shaking, and I turned on the TV, and I learned the tsunami warning. I learned of the tsunami warning on TV, and my phone start alarm. So I realized that I needed to go my office. It was the start of long operation. Then upper right at 16:22, Japan GMA updated the tsunami warning to major tsunami warning for Noto Peninsula because the magnitude is upgraded from 7.4 to 7.6 based on CMT analysis. So GMA upgraded the tsunami warning after the 10 minutes from the initial tsunami warning. Then lower left, at 20:30, JMA continued to monitor the sea level, and JMA downgraded the major tsunami warning to tsunami warning at 2030. Next, 1:15 on January 2nd, JMA downgraded all tsunami warning to tsunami advisory. Yellow color means tsunami advisory. Red tsunami warning, yellow tsunami advisory. Finally, at 10 o'clock, January 2nd, all tsunami advisory are cancelled. It takes about 18 hours from occurrence of the earthquake to cancelling all tsunami advisory or warning. 18 hours. It's a very long operation. Finally, I would review the result of the tsunami following the Noto earthquake. This graph shows the sea level height observed by tide gauge along the coast. This is for Japanese islands. This is Noto Peninsula. The red X is epicenter of the earthquake. Northern part of the Noto Peninsula, very close to the epicenter, the land is uplifted by earthquake. Land is uplifted by earthquake. So tide gauge was exposed above the sea surface. Land is uplifted. Tsunami gauge is above the sea surface. So northern part of Noto Peninsula, sea level observation could not be done. But for example, number 3, Nanaoko, at Nanaoko, tsunami was detected. And number 1, Kanazawa, about 18 centimeter tsunami was detected. This is about 18 centimeter at Kanazawa. The black triangle indicates the time maximum height was observed. Black triangle means maximum height is observed. And violet, red, and yellow bars means the time when the tsunami warning or advisory were issued. You could see the warning or advisory were issued before the large tsunami was observed. But however, number 7, Toyama, the tsunami began to observe earlier than estimate arrival time. At Toyama, the tsunami began to earlier than estimate time. Some research suggested that landslide occurred in the Toyama Bay seafloor. Landslide occurred. The landslides may have been the cause of the tsunamis. Some researchers suggested. After the operations, JMA conducts the field survey to estimate the tsunami height, like this picture, field survey. As shown upper right figures, the tsunami height estimated by field survey, tsunami height estimated by field survey may be higher than observed tsunami height at the coastal tsunami gauge. So anyway, this is the result of the field survey. At Noto Peninsula, where the major tsunami warning were issued, tsunami exceeding the 4 meter was estimated at Noto Peninsula. Even in the point where the tsunami warning were issued, large tsunami are estimated. Currently, about 30 houses were flooded around Noto Peninsula. Okay, this is a summary of this presentation. We think we could issue the tsunami warning as early as possible, but unfortunately, tsunami caused the damage. We would like to continue to work with IOC member states to improve tsunami disaster prevention. Thank you.
Thank you very much. Okay, so we have any question from the floor? Ono-sensei.
Yeah, thank you very much, Shah-san, for the excellent presentation. We were really depending on the JMA's tsunami forecast, and I think you did a great job to issue the warning timely and the big one, upgraded and so on. Then the cancellation is difficult, as you said. Then my question is, your later part, the JMA has many cases already scenario to predict the tsunami based on the magnitude of the earthquake and so on. But when you, as you said, the landslide, induced by the earthquake, that is a different matter. I think that is more difficult to predict the tsunami height. It may come larger than the expected. So how do you deal with that in the future for prediction of the tsunami height?
Thank you. Very, very good question, but very, very difficult question, I think. As Ono-sensei mentioned, it is difficult to forecast the tsunami generated by landslide. It is impossible to forecast the tsunami by tsunami database. At that time, we educate the people that tsunami may come earlier than estimated time. Please keep in mind, tsunami may come at the coast before estimated time. We have to educate with people.
Yeah, thank you. Time and the magnitude of tsunami, yes.
Okay, thank you. Anyone else have a question? Okay, please.
Oh, thanks for the presentation, very, very interesting. And I have a couple of questions. One is, you said that in the procedure, the JMA picks up one scenario for one fault, for one from the database, and calculates the impact, expected impact. But is it just one scenario, the most appropriate, or is just from a suite of a kind of probabilistic estimate of several scenarios? Because we have seen in the previous presentation that the fault database is not so easy in that area. There are several options, district faults and so on. So taking one single scenario, maybe it can be misleading. I don't know. This is the question. And the second one is that when you have updated from the magnitude from 7.4 to 7.6, that is the step that determined then the upgrade from tsunami warning to major tsunami warning. So it's just based on a threshold of 7.5 or something like that.
Okay, thank you. First question, we pick the scenario, when we pick the scenario, we pick the several scenarios and determine the worst case. Pick the several scenarios and determine according to the worst case to issue the worst case to issue the warning according to the worst case. And the second question is upgraded magnitude. GMA upgraded the magnitude 7.4 to the 7.6 based on the CMT analysis. And we researched the tsunami database and according to the magnitude and picked the worst case to issue the tsunami warning. This is the answer for you. Okay.
Okay, thank you very much. I have two questions, but I will talk to you later because we don't have time. Okay, so thank you very much, Mr. Ishida. So let's move to our last presentation of before the break. Professor Koshimura from IRIDeS. He will share a tsunami analysis and field survey of the magnitude 7.5, 7.6, I don't know, Noto Peninsula earthquake.
$7,000. Anyway, thank you for your acknowledgement. So good morning, everyone. I'm Shunichi Koshimura from IRIDeS, Tokyo University. I think I'm sharing the slide. Okay. On behalf of the lab members and collaborators, I talk about preliminary tsunami analysis and field survey of the Noto Peninsula earthquake tsunami. So as the previous presentation from GMA mentioned that GMA issued a major tsunami warning for Noto Peninsula. So this was the first one we received since the 2011 Tohoku earthquake. So in that sense, we recognize that this event has a severe impact, should have the severe impact on the coastal regions. Well, and then observed tsunami height. This is the map from JMA to illustrate which points of the area of tsunami observed. So you see the yellow dots and the blue dots. Yellow dots, the points observed higher than 20 centimeters and then lower than 1 meter. And then the blue ones that are less than that. So from that, the tsunami widely was observed. However, the observed height at the tide gauges are not that high. So looking at this, my first impression that maybe tsunami warning was too much because we only have the observation of the less than 1 meter. However, after running the tsunami numerical models, I changed that my mind that the tsunami warning, the major tsunami warning, was reasonable to thinking about the magnitude of that tsunami attack to the coastal region. So anyway, we started understanding the tsunami propagation and inundation features using the numerical model like that. The first, this is I'm showing here is that the first earlier version of the tsunami source model published by GSI, Geospatial Authority of Japan. So as Professor Ota mentions that the whole rupture, we have the mainly two planes of the fault rupture like that on the left-hand side. With the rupture extended about 140 kilometers by 13 and 20 kilometer wide. So having that, we calculate the displacement field like that. So I think this is the consistent with the observed crustal movement. On the red area is calculated as the uplifted, and the blue area is calculated as subsided. So in that sense, the northern part of the Noto Peninsula was totally uplifted, and then on the side of the Toyama Bay, slightly subsided. So using that, we started the simulation of the tsunami propagation like that. So this is showing the animation, how the tsunami propagates around Noto Peninsula and then attacked to Hokuriku in Honshu region here. So what you read, looking at the videos simulations, we found some remarkable features of tsunami propagation around the Noto Peninsula. For example, how about the directivity of the tsunami energy from the source? I think that the directivity of tsunami energy is dominant to north and south, like that way. So that's why to the south, the tsunami attacked to the Hokuriku region around here. So we expect that the very high tsunami around here. And also around the Noto Peninsula, it's very remarkable. The first point, that's the Wajima or Suzu. The cities, those are cities just inside of the tsunami source region. So that is the reason why very rapid tsunami arrival would be expected. Actually, many eyewitnesses accounts, they reported that the tsunami arrived very fast. And then one more thing is the tsunami refraction. So let me play this again. So after the tsunami is generated, this is refracting all the way around the Noto Peninsula to hit the west side of the peninsula. I thought that this is very remarkable and interesting in scientific point of view. So that is because of a remarkable bathymetric features of Noto Peninsula, around Noto Peninsula. This is the three-dimensional map of the bathymetry and topography published by Japan Coast Guard. This map is looking from the north. And then this is the Noto Peninsula. Here is the source region. And then here's Toyama and Niigata. So after the tsunami is generated, the tsunami tried to propagate to this direction to the south and then to the north. However, because of this, how we can say this? In Japanese, we call that the kaikyaku. In English, it's like a sea spar or something like that. This is shallower, very shallow region with the continental shelf. That is responsible for the remarkable tsunami refraction around Noto Peninsula. The part of that was going to Suzu city like this way. And then the other around here generated, that propagated all the way to the western side of Noto Peninsula, where the Shika nuclear power plant was. So like that, some eyewitnesses accounts at the Shika nuclear power plant. So they reported that about 1 meter tsunami reached at 20 minutes after the quake. That is about 4:35. However, the maximum tsunami, the highest wave, arrived with the 3 meters at about 5:45. That was about 95 minutes after the quake. 95 minutes after the quake, the maximum 3-meter tsunami attacked. So I think this is important. Even in this very near field tsunami, the maximum wave arrives very late after the first tsunami attack. So I think that's the important thing we need to learn as a lesson, that even the first wave is not only always the maximum, the highest. So this is the tsunami height distribution with the numerical model with some measurement and also observation by JMA. So 3 plots. Right-hand side, that is the tsunami height along Noto Peninsula eastern side, Toyama Bay side. And then left-hand side is the Noto Peninsula, along Noto Peninsula on the west side. And then the bottom is the Hokuriku region around here. So looking at here is Suzu City and then Nanao City. So the model of tsunami implied that over 3 meters would be expected, but that's not maximum tsunami height. And also our measurement was pretty consistent with the model result. Actually, after our survey, many groups found higher inundation marks. So this is very part of the survey data. But we found that the Suzu City is, I think, is one of the severe hit by the tsunami, and also by the strong ground motion. And then the other place, Nanao, which is pretty consistent with the JMA observation, with the about 50 centimeters. Looking at the west side, Wajima, Shika, Kanazawa, and then pretty high tsunami at what expected around northern part, and also Shika, all the way to Shika town here, where the nuclear power plant is placed. And then Hokuriku region, also we see the relatively high tsunami at the Joetsu city, where the JMA survey team found about 5 meters or 4.7 meters, the tsunami run up. So in that sense, the tsunami height distribution is very local, but some places were hit by very high tsunami, but the other places are relatively lower. I think that is the one features from this event in terms of the tsunami height distribution. About waveforms. So I'm showing 4 examples of the tsunami waveforms from the top, the Nanao. So I think this Nanao waveform is I think that our numerical model could explain pretty well. And then Kashiwazaki is our model result is a little bit higher than the observation, but I think this is because of the tsunami source that should be improved, especially for eastern part. And then important is Toyama. So you can see that the tsunami model could not explain at all, especially for the first tsunami. So that is because of the landslide. The Japan Coast Guard, after the earthquake, Japan Coast Guard performed the survey, and then they found that underwater submarine 4 kilometers off the Toyama city. This is plot from their survey result. They implied that they found a slump, underwater slump of the 500 meters by 80 meters. That would be the source of earlier tsunami arrival at the Toyama Bay. This is the one. And then for Suzu, one of the very close city from the source region, there is no observation, but from the simulation we can imply that the very first waves comes, but the maximum was after that. So that was consistent with the eyewitness accounts that reported how the tsunami arrived at Suzu City. I will show some remarkable video from to describe how tsunami attacked the Suzu City. So there's at the Suzu City, there's a port, and also along the coast, we have some artificial reefs. So we saw that the tsunami hit the artificial reefs and then to produce the very high splash like that way. And then some of the tsunami attacked to inside the bay, and then part of it penetrated a little inland. So looking at this video, I thought that the tsunami, very high tsunami attack to the coastal region, but after that we found that this is the scene that the tsunami overtopped the breakwater. So, like that, running the numerical model to understand the tsunami propagation features, and then we decided to go to the field to measure that tsunami inundation. So I'll show 2 points in terms of the survey result at the Suzu City. One is the Ida port, and then the other is Ukai fishing port in Mitsuke Island. Ida port. So we found on the coast, some buildings were totally destroyed by the tsunami, and then we measured the flow depth at here at the river mouth, which was up to 2.5 meters. And then the run-up, the tsunami, we found that tsunami run-up along the river, but the inland penetration was not that long. We found that the tsunami trace at about 300 meters from the river mouth. So in general, we found the tsunami run-up with up to 3 meters, but as I mentioned, after this, many survey group surveyed, measured the tsunami height around here, and then they found, some of them found about 4 meters in terms of the tsunami run-up height. And then this is the comparison of numerical model performed with the 10-meter grid. It's pretty, I think it's pretty precise. So the left-hand side is the tsunami inundation line, interpreted from the aerial photo that I think GSI did this work. And then on the right-hand side is the inundation model result. So I would like to ask you about the read, how you read about the model result. I think that's in terms of the inundation area, I think the model will be pretty consistent with the observed one. And the next is
2 minutes.
Ukai. 2 minutes? Okay, 2 minutes. Mitsuke and Ukai. We measured some tsunami flow depth. I thought that this is the first time even for me that the tsunami trace, we found that tsunami trace on the snow. But anyway, so here also the tsunami inland penetration up about 300 meters from the coastline. And then we saw some debris. And that's going to be the base of understand to measure the tsunami inland limit. So at here, this is a comparison of the inundation limit in the numerical model. So like that, inundation area, I think as to confirm the survey from the ground, this line is a little too much. So we support this is more precise in terms of the tsunami inundation zone. So anyway, that's what we have done. And then we're still working on for the source model using the tsunami, observe the tsunami waveforms, and also running the precise inundation simulation to understand the whole picture of the tsunami processes at this event. So this is a summary. The tsunami model result implied the impacts around Noto Peninsula, that is from Shika to Nanao around the Noto Peninsula. And also from the model, we found that the very remarkable bathymetric features at the continental shelf of the around Noto Peninsula are responsible for high tsunamis in Suzu City. And then dominant directivity of tsunami energy was also toward the Hokuriku region, especially for Niigata Prefecture, where over 4-meter tsunami inundation heights were found. The leading tsunami wave at Toyama City could not be explained by the fault rupture, by only the fault rupture. And then after that, the Japan Coast Guard found some landslides for the evidences. And then our post-tsunami field survey, our team, the Suzu City measured the tsunami, and then that was up to, the run-up was up to 3 meter or higher, and then about the flow depths was up to 2.5 meter or higher. So damages in the coastal regions were severe. And then lastly, I think I need to note this. The researchers from over 20 universities and research institutes have conducted a field survey to elucidate the whole picture of the tsunami. And then they are planning to publish the data. So if you are interested, please keep looking at the coastal engineering community from Japan. I think that's all. Thank you for your kind attention.
Okay, thank you. I think we can take some minutes for our break and then some questions to Professor Koshimura. Do you have any question? Okay, can you give him a mic, Don? Oh, yes, thank you.
Yeah, thank you very much for the talk. And I just had a question about if there were any lessons learned in terms of, when you started off, you talked about comparing with the JMA warning that went out. And when you run these models, obviously you're using a much more knowledge about the fault zone and running your models based on that. And how do you have an idea of how that compared with the operational side of pulling one of those models out of the 100,000 database, and whether that fit reasonably well, or the second model, once JMA had the CMT, did that fit better with what you were getting out of your model?
Thank you for asking the question. So I think that is, it's hard to say, but that is the limitation of using the simple rectangular fault model scenarios for the warning. Yes, so actual phenomena is very complicated. So I think the only one is that to run the simulation in real time, receiving the real observation data, including the crustal deformation, even for the offshore tsunami waveforms. Using that, we confirmed that the tsunami model was good. So to use that result for the warning, my suggestion is that to run the real-time tsunami model for the operational purposes.
Thank you.
Thank you.
Okay, Ojal, a very short question and answer.
Thank you very much, Professor, for your talk. The more we observe, the more our observational capabilities increase, the more we learn, the more we identify the landslide component of what we call the earthquake-generated tsunami. And that probably brings the importance of the submarine landslide susceptibility mapping into the question for all the earthquake-generated tsunamis. So what is the direction, and how can we integrate that component into the early warning system, making a thorough assessment of the susceptibility mapping, having a scenario database in the earthquake rupture zone, and integrating that component into the early warning system? Thank you, sir.
Thank you. Well, still, there is a difficulty, even if we have the dense offshore observation network. So, and also the limitation of using the pre-computed tsunami database or based on the fault rupture model. And then one thing we can, I think we can find some solutions to using the real-time observation, like the data simulation. So once we receive the observation or observation signal at the offshore, I think what we can do is to assimilate the model result to be consistent with the observation. So that is my belief that is the only way to solve the tsunami forecast problem for landslide generated tsunami. because we don't have any scenarios in the pre-computed database about the offshore landslide. But what we can do is to assimilate the observation with the models, and then to use that for the forecast. So I think it's the long future, but that is in technological point of view. That's the directions we are now trying to develop. Thank you.
Okay, thank you very much. That's something to think about during the break. Thank you. Anyway, okay, so just to not get behind and lose our field trip, let's continue. Our next presentation comes from Associate Professor Anawat Sapastri from Thailand. He's also from IRIDeS Tohoku University. So the title, Field Surveys of the 2024 Noto Peninsula Earthquake in Toyama, Niigata Prefectures and Characteristics of Casualties. Right? Please.
Okay, thank you, Swadikap. So I thank you for this opportunity. I might skip some slide that has been already explained by other presenters, so to save your time and spend more time on the other slide that might be benefit for you guys. I would talk more about interaction between the engineering part and the social part and damage and things like that. And also, I would like to also give you some introduction about the background of this earthquake, what happened before, what Japan has been prepared for this earthquake before this event. So as you can see here, actually after 2011 Great Japan earthquake and tsunami, 3 years after the MLT Ministry of Land and Infrastructure, Transportation, Tourism, they already re-evaluate the earthquake along the sea of Japan. And actually, yes, as you might know that there are a series of earthquake and tsunami along this side, not only the Pacific side. Japanese people used to believe that tsunami is only for the matters of the Pacific coast, but actually you can see from these records that there are many types of many kinds of tsunami along the west, not the west, but I mean the Sea of Japan as well. And in 2014, so you can see like F and number. So these are the fault that they evaluate in 2014. And yes, for example, near Noto Peninsula, they defined the fault number 42 and 43 and etc. And they did some simulation based on this fault and evaluate the tsunami height. And they already reflected these things to update the hazard maps and also to local government. They also do each prefecture. They also do their own assessment based on this new updated information. And I think I would like to skip this part. It's already similar to what Oda Sensei has been explained, that we have more seismicity before this event. And they mentioned about the uplift, but actually just to briefly explain that also this earthquake also caused a fire in many places, including Wajima and other areas. Of course, uplift in the northern part of the peninsula. Also the liquefaction all the way around in this area, even far east to Niigata Prefecture. And also, as Koshima Sensei has mentioned about the submarine landslide. So this earthquake caused many kind of cascading impacts and damage caused by these kind of things. I think, yeah, so just to make a relationship between these things in one framework. So yeah, as I mentioned, from earthquake create many cascading hazard and impacts. And from my own perspective, the damage to the roads and other transportation countermeasure has delayed recovery and reconstruction. Even right now, some water pipes and other basic infrastructure still under construction or recovery. And this is one of the main things I would like to share to you about the casualties and according to this the earthquake. So there are two types of data set from this earthquake that we can have access from now. One is by NHK. They do an interview with the police department. So asking about the cause of the days there are about 240 fatal casualties by this earthquake. So like this graph, you can see that about, let's say, this 60% were caused by the earthquake, the collapse of the buildings. So they were trapped inside. And but you can see that this 14% of the casualty was caused by the hypothermia or the freezing, so the cold weather. You imagine like today, very big snow, and the situation in the seas of Japan is even more colder than in the Pacific coast. So that is very outstanding point compared to 2011. I will show you in the next slide. And actually, Ishikawa Prefecture, which is the picture of the Noto Peninsula, I believe that this is the first time that the government received the consent from the family of the victims. So they release the information of names and gender and age and where like associate disaster. For example, this person name and then earthquake or tsunami or fire or something like that. So this data only for the family that they give the consent to disclose this information. And for this one, we have around 140 data. But again, similarly, you can see that about 80%, more than 80% that people were killed by the earthquake, and only 2 people in this data from tsunami. So, as mentioned, I think Mr. has already mentioned that. Yeah, for earthquake perspective, you can see that even you might think that Japan has very good advance in protection or earthquake resistant, but in this area, when I search for the ratio or things like that, Ishikawa Prefecture, they have very low ratio of earthquake-proof buildings. So that's reflect to this kind of data as well. So and also like this 14%. People who got died by the freeze or hypothermia, so they might survive under the debris, but because of the road damage and takes time for the rescue, they could not survive because of the very cold temperature. So I think this could be improved as a big lessons. Similarly, this is as I mentioned, when we compare to 2011 or the 1995 Kobe earthquake. We can also see that the drowning by water was dominant in 2011, but not at all for the hypothermia. It's very dominant here, but not for other two earthquake. Even though this one, the Kobe earthquake, was also in January in the winter. So again, this time I think the countermeasure for especially this big disaster in the cold winter, and of course in the summer, of course, heat stroke also very important. So this kind of thing, I think this data also tell us a big lesson as well. And yeah, so this is also they already mentioned about the uplift, but when we talk about tsunami, so I would say for us we were lucky in that sense of tsunami. So because this land is uplift, so there was less tsunami reported in this area. And also, yeah, we also did similar simulation. So as Koshima already mentioned that it takes time from the source to Toyama. And then we also observed that in Ukai area or near Ida Port, the wave from the south and north came at the same time and merged and then and enlarge the inundation in this area as well. So we can also observe this kind of phenomena from the simulation. I think this one I will also skip the things about the early arrival wave of observed in Toyama. So I think I will skip this. And similarly, we'll skip this. So yeah, we also try to simulate the landslide, and we found that having landslide in the bay could also help to reproduce the tsunami as well. And I would like to point out this point that actually this kind of phenomena is not the first time. In 2007, again, in Noto Peninsula earthquake, the fault, oh, sorry, let me put the pointer. So the earthquake is here, the fault is here, but we also observed tsunami in Toyama area as well. So again, so this author, they do the inverse simulation and they suspect that the fault, there should be some submarine landslide around this area as well. So again, this is not the first time that this kind of thing would happen. And one of our colleagues also, I think 1 or 2 years ago, they also start doing some assessment of the possible submarine landslide trace along the Japan Sea side as well. So it's still on progress, but just to share that what we have learned and done so far. And the thing I will skip. How many minutes did it? I think how? Okay, good, thank you. I will just go through the rest. Yeah, for tsunami damage as well. So you can see some location where we have building remain and tsunami reached around like 300 meters from the sea. So, and also damage to the fishing boat as well. And this is kind of typical damage by tsunami. And this is for JMA data. We'll just skip again. For us, so as I mentioned about the submarine landslide, so our team, we mainly focus on this part. So Toyama Bay or Niigata Prefecture, we went there a few days and did some measurement. And luckily, yeah, so because this event happened still before the sunset. So there are many CCTV cameras on the coast and yeah, so many this kind of videos, so we could have a chance to check. And for example, this is one of the famous tourism spot in Toyama Prefecture. I'm not sure if you know about that, but for example, just before the earthquake, there are many tourists here, but right after the earthquake, they're all gone. They already evacuated. So that is very good signs that they have very high awareness. I was very worried about like they might stick into the lesson from 2011 that they might have 30 minutes or 1 hour to evacuate, but by seeing this kind of video, I can observe that they evacuate very fast. And yeah, so we can see that during the maximum tsunami overtop this rock, so we go and measure things like that. So this is what we can do at that time for the survey. And our team, we keep looking at the debris along the sand beach, or this one, we just follow some YouTuber and they go right after the cancellation. So yeah, we try to do this kind of, making use of this kind of available publicly access data. So for our team, I think this is similar to what Koshima Sensei has mentioned, that we are gathering the data. This is only the data from our team. So we observe in Toyama, the tsunami is more or less small, like 1 or 2 meters. And then we also observe similar to other team that in Niigata Prefecture is about 3 or 4 or 5 meters. This is a bit more higher. So like this. So this is my conclusion. So might be similar to others that we have observed tsunami from small place in Toyama, 1 or 2 meters, but others could be 4 to 5 meters. But again, I'm glad that we can observe that they have high awareness, and also we have very few death by the tsunami. So that's a very good sign of education or activities. But still, I believe that for the earthquake perspective, the earthquake-proof building, things like that still should be done. And also similar to Koshima has mentioned that and also presentation by GMA that this time the tsunami takes so long, so people had to stay in the shelter very long in the cold winter. So that is kind of issue that we still have to be improved. And you can check our for more detail in upcoming publication. And this is my last slide. So again, so we are now collecting all the data together. And yes, so please have a look at this website. I don't know when, but yeah, so I believe that we will upload our survey results and other information in this link. I think that's the end. Thank you.
Thank you very much, Professor Anawat. Okay, can we have questions from the floor? Any question? No? Should I ask? I know the guy, so I already asked him many things. Okay? Okay, maybe I should ask you something. Okay, how are you? No, okay. So I was wondering about the data of the casualties. So how did you compile that information? Is that right now open information you mentioned?
For Noto 1, yes. For NHK, you can see from the website. If you want, I can send you the link. And Ishikawa Prefecture website also, once they have the update, they will post.
But as you say, it's not the entire number of casualties, right?
For Ishikawa, yes, only those who got the consent from the family. But for NHK data, I don't know how can they ask the police.
Because this is not a common way to do things, I guess.
Yes.
But is it gonna be like that? You know, if it's gonna be like that from now on, or is kind of a new policy, or
I'm not sure
what happened to this time then?
Yeah, that's also my question. But like, I'm surprised. I mean, for NHK, they could have right to interview or ask the police department. But for Ishikawa Prefecture, I still wonder why they have decided to disclose this kind of data. But it's good. I think maybe they think about it's good for countermeasure in the future. Maybe just my guess.
Okay. Other question from me? Any question from you? Oh, Bruno. Okay. You can take the mic there.
Thank you for your talk. So I have one quick question. You show one slide, cascading effect after this earthquake. So could you explain a little bit how you come out with this process, or is it based on the news, based which information?
Yeah, so just keep reading news and try to understand what was happened, and link them together. Yeah, so just read news and what happened, why it was happened, things like that. Thank you.
The part of the answer for the government tend to be a bit too careful for disseminating the information of details of the people who died, the name, gender, and so on. Usually it is. But in this case, or the emergency time, they also want to share the information, because many of the people, maybe relatives, family members, or the friends, they want to know what happened to the people in there. So in some cases, disseminate information like that. Or deceased people, the information you see, and then sometimes the newspaper as well. And as long as it is agreed by these family members, so that is the case. But it is not easy to get that information. For the I'm into the loss and damage statistics work, and in many places, the privacy reason they don't want to share the information. That's a general policy, but sometimes shared with like that.
I have a question there. Ono-sensei, can you take the mic?
Thank you, Anwar, for the nice presentation. Just a questions. When did you go to the field? I mean, how many days after the event did you go there? And what are the challenges in terms of course, the cold weather is the challenge, but whether there is difficulties in actually tracing the remnant of the tsunamis and so forth?
For us, we believe that the traffic condition will, as you can see from the map, is very isolated area. So we decided not to go that soon. So we went around the end of January, so about 3 or 4 weeks after. But luckily we brought sunshine from Sendai, so we were quite warm at that time. But yeah, I think that the challenge was there are two challenges. I mean, for like Koshima Sensei team who went to Noto Peninsula, the challenge was the traffic that the road has been damaged and it's take a long time to go there. And for us, the challenge is that tsunami was not that high, as you can see from this slide. For example, it's only like some debris along the coast. So like this, of course, you can see from CCTV camera videos, but we are not sure, is it exactly this point, this debris or something like that? So we also have to ask people nearby or something like that, or watching from the video as well. We know that tsunami climb up to this step, so we go and measurement. So for small tsunami, I think that's kind of challenging. Yes, but luckily that it happened in the daytime just before the sunset. Thank you.
Okay, thank you. So it's time. Let's move to the next presentation. Shall we give a round of applause? Did we already? Okay, next presenter is Associate Professor Eric Mas, which is me, from IRIDeS. Sorry? It's fine. I can moderate myself. My presentation is Population Dynamics with Mobile Spatial Statistics during the 2024 Noto Peninsula earthquake. Is it okay? Okay. Thank you, Mr. Chairman. This is my team. We're working in what we call, well, we don't call, but it's called Mobile Spatial Statistics. So probably international people might be a new term for you guys, but I'm sure you know about GPS track data. I mean, using the mobile phone GPS information to track population flows or location of people, right? Mobile spatial statistics is actually developed by Docomo Insight Marketing. Docomo is one of the major carriers of cell phones and others, internet, whatever, in Japan. And in a nutshell, what they do is we have all these towers, like communication towers, right, or base stations. And whatever device that it connects, Wi-Fi connects to that tower, right, is logged by Docomo. And because every device or each contract, let's say, is linked to a individual, a person, they can know what are the characteristics of the person, right? And then, but actually to protect the personal information, what they do is they aggregate, let's say, all this information in a specific geometrical space, like this. Like the aggregation method is, let's say, in 1 hour, this person has been connected for 30 minutes, so it's counted as a half of person, right? This person in 15 minutes, so is one fourth, and then you aggregate all of this. So we are not having information specifically for each person, name, whatever, right? Is the information of an aggregated manner. And also, because they have like the information of their market share, like let's say how much of in this area of how much of customers based on the population, how much customers I have, so I can extrapolate to the other customers from other carriers or from other kinds of that are not in my I don't know, market share. So they statistically extrapolate that information to account for the population. Generally, the population that is users of devices, right? Like 15 to 79 years old. So we assume that these age ranges are not included, right? So so the information we can receive is by prefecture municipality, a 1 kilometer mesh, but the one that we are using right now is a 500-meter mesh, okay? And is on a temporal resolution of 1 hour, okay? So the idea of this is in 1 hour for the whole Japan, every hour, let's say, you can aggregate or by the 500-meter mesh, you can know where population is, how many people is, or like population spatial distribution, right? How many people is in certain locations, right? So you can see the changes, let's say, I don't know, like for Golden Week, this special kind of holidays we have, how people move around or how much changes you have. But you can go as much resolution as you want, like because we have 500 meter mesh, right? You can focus in specific areas or inundation area, or possible inundation areas, or cities in general. So the information is very granular, very detailed in that sense. So what can we use this information for in disaster management or for disaster purposes is one of the main objectives of our exploration right now. For the Noto case, what we have is these target areas for analysis. We have focused on these 4 cities and towns, which is Wajima City, Suzu City, Noto Town, and Amiso Town. Okay, you can see here the 2020 national census, which is around this. The main area of population is around here. So you can see that there's a lot of like mountainous areas, very few people. But if we look at the information of the mobile spatial statistics just 1 hour before the earthquake, let's say this is calculated in a range. So it's the aggregated population from 3 p.m. to 4 p.m. Okay, so in this time slot, this is the distribution of population, right? So you can see that in Wajima there's a lot of people, and Suzu also there's a lot of people. Also, this is the human losses. This is the basic population, but the number of deaths. So that's why, and what I guess he mentioned 140 people in his statistics that we can get easily. But as we see, there is a little bit more. Probably we don't have consents from these people to release the names. So this is the area that we are focusing. So why we are focusing on this area? Well, it's basically because, of course, the earthquake main shock was around here. And also because there was a power outage, okay, around this area, and in some areas it's still continuing. And we were concerned that the power outage actually may influence the base stations or actually the information that we have from mobile spatial statistics. So so you can see here that this is the number of power outages houses or households that they had. And this is information from NTT Docomo at maybe 1 hour or less than 1 hour after the earthquake, okay? Which shows the coverage, current coverage of their carrier, right? And I think it's the areas that are not covered are in green, some kind of green, right? So, but the thing is that actually we got to know that if there is not physical damage to the base station, to the tower, there is an emergency battery that actually works for 2 or 3 days more, right? So the information will not be affected if there is no physical damage to the base station. Unfortunately, we cannot get information of the specific location of or status of each base station due to, I don't know, privacy concerns maybe from the carrier. But what we can get is just kind of this information to let us know, okay, the area that we can focus is still has some kind of signal, okay? So what we did first was a kind of overview. So first we aggregated for each city and town in the whole area. So as you see, for example, Wajima has a very small center of the city, but the whole administrative area is bigger. Okay, so we aggregated all first, okay? And as you see, and then we compare that to this is 2023 and 2024. So 1 year before on the same day, okay? On the 1st of January. What is the trend? So if you see in the hours, the trend is very similar until the earthquake comes. So this is before the earthquake and this is after the earthquake. So after the earthquake, in Wajima, Noto, especially, we saw this kind of drop down, okay? So in some other areas, the drop down is not so easily watched, probably because we aggregated a lot. It's a big area analyzed, right? But also, so how can we interpret this? It can be many things. It can be movement of people, but also it can be the effect of power outage, right? Because probably the probability that people from, I don't know, let's say Anamizu, I don't know, from Anamizu in 1 hour moved out of Anamizu is probably few, right? So maybe there's a lot of influence of the power outage. So the main thing that we have to do is maybe localize a little bit our analysis. So we move that to here. And looking at each city, what you have here is, again, from 2022 to 2023, this is the blue one, right? And the red one is this year on the earthquake time. So you can see that the trends are very similar before the earthquake. And there's a peak also in last year, because it's end of the year, so people go back home and then they go to this area. So the trend is very similar. But after the earthquake, you can see that the trend, for example, here keeps going down. So this is clearly an effect of the earthquake. We can compare that also, especially by plotting the mobile spatial statistic information, comparing that to the intensity of the earthquake, and then creating kind of a risk map where are the major population that experience the higher intensity of the earthquake, right? And of course, it's in the center of the city. So the same we do for other areas like Suzu City. Again, Suzu City has the same trend as Wajima. Like after the earthquake, the population distribution goes down and keeps going down. So this is characteristic to the areas that are very close, Wajima and Suzu, that are larger than the other ones, but also very close to the fault of the source of the earthquake. But if you go to Noto, for example, the trend is a little bit different, right? There is the big drop after the earthquake, but then kind of it recovers fastly, right? It's probably that people came back faster to check their probably damages, or base stations were rapidly recovered, right? But at least we can see that the trend kind of stabilizes a little bit. So we can kind of monitor a little bit how is the recovery or reconstruction here if we keep looking at this information. If you look at Anamizu, it's kind of the same. In general, from 1 year to another year, there's a reduction of the whole curve, probably because of aging, right? But in general, the trend is very similar. In New Year's Eve, it comes up, but after the earthquake, it drops a lot, and then it recovers a little bit, but it doesn't recover too much as the level that it's supposed to be recovered based on past patterns, right? So if we keep going here, we can see that there is here the population changes after the earthquake from the spatial kind of analysis. So we focus now in the specific small centers of cities and towns. And if you see here, for example, if it's blue, there is a 100% decrease of population, 100 persons decrease of population, and if it's red, there are more than 100 persons that were increased in the times before and after the earthquake. Okay, so you can see here that blues are kind of close to the sea, and reds are kind of to the inland, right? At least, for example, Suzu, Wajima, sometimes. These points are the evacuations buildings. Unfortunately, like because of the resolution, in one 500-meter mesh, you will have like 2 or 3 evacuation buildings. So sometimes it's not easy to see what's going on in the evacuation building or the evacuation shelter. But what we can see is that there's a declining population trend in coastal meshes and a population growth trend in inland meshes, which suggested 2 things. It can be that actual evacuation occurred, right? Or it can suggest that there were more damage in the coast that probably affected the towers and not in the inland area. So it's something that we have to verify. If we look this in not a spatial but time series case and divide this based on the elevation of using a digital elevation model, and we divide the meshes by which meshes are in over 10 meters and which meshes are below 10 meters, right? Now the 10 meters is just an arbitrary use. We can now that we know the field survey, we can make 5 meters, let's say, because it's the limit of inundation runoff. But in general, if you see for over 10-meter elevation, after the earthquake, there's a big increase, meaning that for areas in higher elevation, there's a higher increase of population, which makes sense if we expect people to evacuate there, right? And then it's a big reduction in the lower areas, but then lower areas come up kind of come and go. It looks like probably people return, but then kind of they cannot stay there for a while. So probably some kind of aids or aiding, like people who were supporting the reconstruction recovery. And also here you can see that there's a decrease of people, but probably the trends are not really going back. If we keep going, looking at this, then we probably see that at some point, hopefully, this is going to return to the original patterns that they had before. If we compare this to the tsunami warning, so number one is the earthquake and tsunami warning, right? That actually was raised at this time, but is in the same time slot. And then on two, it was reduced, right? So in general, the kind of shapes, it goes along with the tsunami warning, which suggests a little bit that actually tsunami warning was one of the triggers of these changes, maybe. Okay, so in conclusion, in Noto town and in Anmisu town, it was observed that the flow of people had returned to kind of normal trends in about a week. However, for Wajima City and Suzu City, which are closer to the epicenter, and actually those who had more casualties, have yet to see a recovery in the flow of people. The population in low-lying areas clearly decreased, upland areas increased, so evacuation to higher ground was facilitated by the issues of major tsunami warning, maybe. And in our future discussion, we expect to do more analysis of regional factors, include much more information to see what is the influence of this geographical bias of the population distribution in the time, right? And also, well, we hope this information can be used in real time to kind of detect some anomalies in population or detect some kind of population exposure before an event will happen or can happen. So we can have a much more detailed or significant information of people, okay? Okay, so that's it. That's all my time. Thank you. Okay, if you have any question for Eric, you can ask him. I cannot ask myself, so you guys have to ask me. All right. Okay.
Thank you for your talk, Eric. Since your data is very dependent on having your towers functional, were you able to get your hands on information from the telecoms on what towers were damaged and when and how they were repaired? Because I think that would be very interesting to see in your analysis.
Yeah, actually, that's a good point. We actually had a meeting with them. But the most we can get from them is kind of this information, which is not that bad in general. I mean, it would be better if we have like specific information of each tower and the location of them, of those. But at least this information, what allows me is like, especially just locate which regions at which time they don't have service. So probably just to take out those meshes out of my analysis, which we haven't done for this yet. But this is kind of the information we hope we can use right now, and it's usable because this is a public web, so we can actually access this anytime. Okay, anyone else? How's my time? Is okay? Okay, last question, very short.
Hi, thank you very much for your nice presentation. It's a very promising technique. So I was wondering if, in terms of resolution, both spatial and temporal, have you learned if there is the chance to get it at a higher resolution? Because I'm thinking, as you mentioned, for real time and for some kind of studies, maybe 500 meters of spatial resolution or 1 hour window time is maybe too big, too much.
Yeah, as for the resolution, spatial resolution, one thing that we have to consider is that this is based on towers. So of course, in highly populated density, urban density areas, there are more towers than in non-urban areas. So there is more bias there. And 500 meters is still a high resolution compared to the tower's distance, right? So the reliability on 500 meters is not that much as compared as you aggregate to a bigger area. And in temporal resolution, I guess it's possible to get more than 1 hour. Like the guy with the money will probably get us 10 minutes, right? So hopefully we will get a much more temporal resolution, but still the analysis has to be dependent on that spatial confidence. Okay. Okay, there's no more time. Thank you. Thank you, Eric. Let's move to our last presentation. This is mine. This is mine. Where is this? Yeah. Okay, our last presentation comes from Associate Professor Bruno Adriano. He's also from IRIDeS University. Analysis of the 2024 Noto Peninsula earthquake using remote sensing imagery. Okay, please.
Thank you, Eric, for the presentation, introduction. Hello. As Eric said, this is a slightly different view of the Noto event. We will use Earth observation data to try to analyze or try to see what happened with especially focusing on the building damage. And this is the team that conducted this research. And here I'd like to point out that this work was possible because we have two great students, Ruben and Cesar, that are sitting over there, that contributed a lot for the analysis of this data. So let me begin by acknowledging that this study, or all the products that you will see now, was done or was possible because most of the this institute released the data by free. So now this data is free, and I think everybody can reproduce this result that you will see here. So first, here I show the PARSA-2 EROS-2 data from before the earthquake. This is from June 6 last year, almost 6 months before the earthquake. And this is the condition at that moment. So one thing that we need to know when we look at radar data is that radar data observe the Earth observe more of the geometric shape of the Earth. So it's based on the roughness of the Earth. So areas with almost a flat surface, like the ocean, it have very low intensity, darkest areas, and areas with some artificial structures or mountainous areas show some brightness in the area. So that is how we analyze intensity SAR data. If we see some changes in the intensity before and after one event, in this case, the Noto tsunami, we try to understand what happened. So this is before the earthquake. And this is after the earthquake. This is 1 day after the earthquake. And then you can see some changes, right? Right, but looking separately, it's a little bit hard to see. So first we combine those data sets into one color composite. And the way we combine here, the blue color indicates the intensity of the data has increased from before to after the earthquake. And red or reddish color areas indicate some decrease of the intensity. So we can infer that if there is some increase, that means something has appeared after the tsunami, and some decreases, some buildings or something have been removed or changes, right? So if we look at here, we can see some aspect of the overall overview of the earthquakes. If you look the west side of the peninsula, I'm not sure you notice, but there is some blue color intensity, right? Which indicates some increase of the intensity. And this is consistent with the uplift that was reported or was observed in this area. And if we look to a spot, the Nafume Port and Wajima City, we can see here, some increase in the SAR intensity, both areas. And like again, this is due to the uplift in this area. But if we look to the east side, in Susu, that we've seen a lot, it's been mentioned a lot during this seminar, almost no changes. Probably we can see this structure slightly damaged, or it changed to red, maybe because it was damaged, or at that point the water was, the sea level was higher than this. But anyway, we can see the uplift. The uplift is clearly observed. And also we can measure that in this particular point, for instance, there was one increase of one horizontal gain of the land, about 100, 120 meters in average. And if we see here in Wajima City, I think it was mentioned, there was one big fire in the center of the city. And it's also detected here as a red color. So most of the building in here was wooden houses that were burned down. And let's say the roughness of the land at that point, it reduced. So it represented here in the red color. And also, if we look at the eastern side, if we see the pixel level inside the inundation area reported by GSI, the Geospatial Information Authority of Japan, we can see some bluish colors appearing here, right? So that indicates some increase in the SAR intensity. And this might be due to after the earthquake or after the tsunami, some debris was accumulated in the area, generated some sort of roughness. So having this overall view of the damage, we wanted to analyze more in detail, so individual buildings. So using SAR data, although it's very useful information, especially for emergency response, we cannot see particular buildings, right, because of the resolution. So unfortunately, thanks to the great job of the GSI, they conducted a field survey campaign and took several aerial photos and the whole peninsula, and they quickly released it online. So we got that data and we start to analyze this in more automatic or systematic way. So for that, we use what is currently machine learning algorithms, specifically convolutional neural networks. And I will show briefly our approach, but later I will share some papers that you can refer for further details. So this is our methodology. So assuming that we can always collect aerial photo, high resolution aerial photo before the earthquake, right? We always have Google Earth. And once we get the post-event aerial photo or aerial image, we can use our model, in this case, one CNN-based model, to detect or to map automatically the land cover map, right? And having the land cover map before and after the event, we can conduct some sort of change detection analysis. And of course, if we have the footprint in the area of interest, it helps, although our model also is able to delineate the footprints and other features of the land. We can integrate this information and map the buildings that are changed, in this case, particular buildings that are changed after the event in the tsunami. And below you see just a quick look of the architecture we use. And we can also do this for the building, focusing only in the buildings. And this is the data set we use to train our network. So this data set contains a high resolution submeter level for several cities, regions around the globe. And one thing to notice here is this network didn't see any image from the Noto Peninsula. It's completely out of domain application of this network. So this is all the methodologies. So if you like to see more detail of the network or the training process, I invite you to read these papers from our group. And on the top, you can see the 2 papers of our students, Cesar and Ruben. Okay, so with that advertisement, let's see the results. Okay, so this is the pre-event high-resolution image from Google Earth, right? I show because the time I'm showing only Suzhou city, since once when the city was heavily damaged. Yeah, this is the condition before the tsunami hit this area. And this is the aerial photo after, 1 day after, right? Taken by GSI. That we compare the before and after, we see several changes or several product of the tsunami, right? So for instance, around the river mouth, there is some sort of debris or the water coming here. And there is also here, the buildings have been were washed away by the tsunami, these areas. Also a little bit more inland, there is some damage, building collapse, probably due to the earthquake or the ground shaking. So having these two high resolution images, we can see specifically, we can see each individual building, right? So we apply our network, our AI model here, and we map the land cover. This is the land cover before the tsunami into 8 classes, right? As you can see for the legend here, the red segment represent the buildings. These white long segments represent or map what is the roads, and the water is blue, and these gray segments are impervious surface beside buildings and roads, right? So this could be pavement or pedestrian path or something like that. So this is the land cover for before. And if we look, we apply the same model to the post-event aerial photo from GSI. This is what we get. If we see the before and after again, we can see very clear changes. For instance, this building here, this long building, it changes its classification. That means something happened to this building. So probably it collapsed, and the new surface is covered by some debris or vegetation. It's mapped as a vegetation in our model. And this, for instance, in this part, before, we could map kind of accurate the road here, right, and the buildings. But after, the road change the conditions, change its characteristic to pavement or debris or something like that. And this model also can detect that some rope structure and probably due to the collapse or the debris produced by the buildings. So with these initial results done automatically, we start to look more into detail in the buildings. So we try to compare building by building, and also thanks to some companies that release aerial photograph in oblique much close range and oblique angle, we compare even building by building. And this is some examples of the damage of our evaluation. And at this point, we decide to do the analysis for the whole peninsula, and we download, we got the building footprints from GSI. As you can see here, initially we focus only in the tsunami damage, but after that we expand for the whole peninsula. And I think I'm going too fast. This is the visual interpretation result. So to do this, we actually deploy the full might of our laboratory, actually led by Ruben and Cesar, and we evaluated more than 130,000 buildings, probably in a few days, less than 1 week, I will say. And this is the result. So in some areas, because we only have aerial photo, we focus only in 2 damages, destroyed and survived. But in some areas, we have access to oblique photos. We could also categorize in a more discrete damage, right? Right, and then this is the analysis or the overall, some statistics for some areas that I was showing before. So we can see here that Wajima City, the ratio of damage, it's almost 10%, 77%, and so on, right? So using this data set with support also of GSI, we launched online mapping. So we built this GS web server to try to get feedback from the people, or other person that in the affected area to try to correct our initial analysis. So far, I think we got about 100 points as a correction, and this website, of course, is online, and it's supported by GSI. So, okay, maybe I went a little fast. So almost finished my talk. So to summarize, I show this map. This map shows the comparison of the building damage against the tsunami height at the coastline. And for the building damage, we run a kernel function and to try to see where the damage are accumulated. So if you see here, of course, the damage areas with high density of building damage is sort of correlated with the tsunami height at the coast. But for instance, in this case, for Susu area or around Susu area, we have extreme concentration of destroyed buildings. Like I say, although it's correlated with the tsunami height, but also there is some effects here that we should consider, such a landslide or also damage due to the ground shaking. So we are exploring now these sort of results. And yeah, to conclude, we also, our students are now working very hard to summarize these results in a paper. So hopefully, well, next month we can submit the preprints. But yeah, so our further discussion is like this. Of course, we need to validate our initial building damage interpretation. So we actually, at the beginning of this month, we went to the field survey, and then we verified that our analysis was correct in some areas, but in some other areas that probably due to the occlusion of the satellite image or lack of information, there was some misinterpretation. But yeah, we are correct, and that is why we launched the online mapping. Yeah, but another point is more further discussion in the understanding the relationship of the ground shaking and the severity of damage. So we are thinking, of course, tsunami fragility also a lot of fragility functions here. And like I mentioned, or if you remember the previous slide, there is also some local soil conditions that should be taken into account to understand the fully spectrum of the building damage. And yeah, actually, this was not the first time we conducted this analysis using remote sensing data and machine learning. We have the experience also of the Turkey earthquake. So from that, we are trying to implement this all algorithm in a more systematic way for the very quick early emergency response. So that is my talk, probably a little bit fast. Thank you for your attention.
Okay. Thank you very much. Okay, so we have some minutes for questions. Oh, okay, please. Can you take the mic that is here? Please turn on the mic.
Oops. Thank you for sharing. Sorry. Thank you for sharing your work. It's marvelous to see. My question here, I think this is very useful also, like in every, for the damage assessment especially, because like you show in your result, temporary before you have verification, that the figure of the damage you classified into two, right? Destroy and survive. My question here, is there any criteria for the survive building and criteria for destroy building? Because I know this is tsunami and then it's quite difficult to do that, but I would like to know. My second question here, whether this can be applied for the earthquake, which is in the inland, not in the coastal area, because this is very useful, especially for the, the rehabilitation reconstruction program using the very quick damage assessment. So this is my question. Thank you.
Thank you for your question. Okay, so for the first question, maybe it's two parts. Like I mentioned before, first we started with the automatic mapping using machine learning. And in that case, the criteria is to see if the building or the segment building changes from before and after. So if the segment for the building drastically changed, like disappear, yeah, we consider that as a damage, a building that being damaged. But when we move to the more detailed analysis using aerial photo or oblique photos, yeah, we try to look for more aspects. Like, you know, that one of the probably limitation of optical remote sensing is that we only see mostly from the almost perpendicular nadir angle, right? So we can judge only the damage based on the condition of the roof or the surrounding, right? So we don't see some destruction on the facade or the building facade or something like that. So that's why we use sort of multi-source information with oblique photos to judge those areas. And for those areas that we have that information, we conducted, yeah, it was possible to do more than 2 classes, 4 classes, I believe. So for survived building, partially damaged, heavily damaged, and totally wash away or something like that. What was the first question? The second question is, yes, yeah, as you can see, like I said, we focused initially in the tsunami affected area, but then we moved to the whole peninsula. In the whole peninsula, there was another range of type of damage, or the earthquake, the ground shaking. There was also due to some landslide and the fire, of course. Yeah, both approach, I mean, the combination of this machine learning base and the individual visual inspection, yeah, it can be used for all different type of different disasters.
Okay, thank you. Do we have any very short question, comment, claim, suggestion, advertisement, whatever?
Thank you very much. You mentioned about the Turkey earthquakes, the type of collapse, the pancake collapse. Was this a problem for you, or were you able to even solve that with the oblique approach? Thank you.
Yeah, thank you for the question. Yes, that's actually one good question. Yeah, in case of the Turkey earthquake, the pancake collapse, we were able to detect those buildings because the pancake collapse generated some debris around the buildings, right? And that debris, it changed the land cover in the building. And once we do the, like I say, matching before and after, yeah, there was some changes. So we could detect those pancake collapse.
Okay, I think that's all for this. Thank you, Bruno. Okay, please. Okay, so we reached the end of our seminar, but before we would like Bernardo Aliaga, can you make us the honor to close the seminar with some remarks? I think you can take the podium there. 5 to 10. If you talk like Ono Sensei, maybe 5 only.
Thank you, Eric. And many thanks to all colleagues, and in particular to IRIDeS for hosting this workshop and organizing the field trip that will follow. I'd like to thank you, Professor Koshimura, for his generosity and for his thoughts about early warning and the future for forecasting tsunamis. This workshop, of course, shows the richness of research approaches to tsunami hazard. And I'd like to just add to all what has been said that for preparedness, it will be also important to probably know more about the recurrency of events in the same area. And just as we went awake on 1st January in Paris, Oshal and I started to exchange emails about what was ongoing. And we note that records of similar events have been found near Vladivostok in geological records. So we started to look at the sea level stations in that area that were not available at 8:38 a.m. And they became available half an hour after. And I just got to know a couple of weeks ago that these sea level stations were actually functioning, but the URL of the stations had changed a couple of months before. So a colleague working in Ostend had to fix that immediately, and the records of this sea level station became available for the other countries in the region. So just to mark once more the importance of international and intergovernmental cooperation for early warning on tsunami warning systems. With that, I want to just say thank you again, and thank you very much to all for listening.